Welcome to DAR Tutors for online and home tuition. In this video, we will explore the fundamental concepts of probability, a key topic in IB mathematics, applications and interpretation higher level. Specifically, our learning objectives are to understand what probability is, distinguish between experimental and theoretical probability, use two-way tables, Venn diagrams, and sample spaces to represent possible outcomes and find probabilities, and solve complex problems involving these tools. Probability quantifies the likelihood of an event occurring. In mathematics, this likelihood is assigned a number between 0 and 1, inclusive. An impossible event has a 0% chance of happening, which corresponds to a probability of 0. A certain event has a 100% chance of happening and is assigned a probability of 1. All other events have probabilities between 0 and 1. This scale shows how we can interpret different probability values. For example, a probability near 0.5 indicates an equal chance of happening or not happening. We can determine probabilities in two main ways: based on the results of an experiment or based on what we theoretically expect to happen. First, let's look at experimental probability. This type of probability is based on observing the outcomes of an experiment. The number of trials is the total number of times an experiment is repeated. The outcomes are the different possible results of a single trial. The frequency of an outcome is the count of how many times it occurred. The relative frequency of an outcome is its frequency divided by the total number of trials. When the number of trials is large, this relative frequency becomes our best estimate for the probability of that outcome. This is known as experimental probability. Let's consider an example. A small cone is tossed 279 times. It lands on its side 183 times and on its base 96 times. To find the experimental probability of it landing on its side, we divide the frequency of side outcomes by the total number of trials. This gives us 183 over 279, which is approximately 0.656. For it landing on its base, we calculate 96 over 279, which is about 0.344. Notice that these two probabilities add up to 1, as the cone must land on either its side or its base. This demonstrates how to calculate experimental probability from observed data. A key principle to understand is the relationship between the number of trials and the reliability of experimental probability. The law of large numbers states that as the number of trials increases, the experimental probability will approach the true theoretical probability of an event. Consider a simulation where we roll a fair six-sided die and track the relative frequency of rolling a 2. If we plot the relative frequency of rolling a 2 against the number of rolls, the graph would fluctuate quite a bit for a small number of trials. For instance, after 20 rolls, the relative frequency might be 0.1, but after 40 it could jump to 0.25. However, as the number of rolls becomes very large, like 1,000 or more, the relative frequency line will smooth out and get closer and closer to a horizontal line at y equals 1 over 6, or approximately 0.167. This demonstrates that a larger number of trials provides a more confident and accurate estimate of the true probability. Now let's apply these ideas to some IB-style problems. A common type of problem involves two-way tables, which summarize experimental data. Here we have a table showing the number of short-term visitors to Australia during 3 months in 2018, broken down by their main reason for travel. Part A asks for the probability that a person who visits in June is on holiday. The question specifies a person who visits in June, so our focus, or sample space, is only the June column. In June, there were a total of 308,300 visitors. Of these, 150,600 were on holiday. So the probability is 156,500 divided by 308,300, which is approximately 0.50. Let's look at Part B. Estimate the probability that a person who came in the period April-June arrived in May. Here, the sample space is all visitors over the entire 3-month period. We must first find the total number of visitors by adding the totals for April, May, and June. This gives us 890,700. The number of visitors who arrived in May was 260,900. Therefore, the probability is 260,900 divided by 890,700, which is about 0.293. This shows how crucial it is to correctly identify the sample space for each question. A key skill in HL probability is to use two-way tables to find complex probabilities. Let's look at another worked example. This table shows survey results about a new theme park ride. People were classified by age group and whether they liked or disliked the ride. The first step for any two-way table problem is to complete it with row and column totals. The totals are calculated by adding the frequencies across rows and down columns. This gives us the total number of people surveyed, 130, and the totals for each category. Part A asks for the probability that a randomly selected person liked the ride. We look at the liked the ride total, which is 83, and the grand total, 130. The probability is 83 over 130. Part B asks for the probability of a child who disliked the ride. This asks for the intersection of two conditions. We find the cell where the row disliked and column child intersect. This value is 17, so the probability is 17 over 130. Now for part C, which is often more challenging. Find the probability that a randomly selected person is an adult or disliked the ride. In probability, the word or means at least one. So, an adult or disliked means the person is an adult or disliked the ride or is both. We can add up the frequencies for the people who fit this description. That's the 28 adults who liked it, the 30 adults who disliked it, and the 17 children who disliked it. Notice we do not count the adult dislikers twice. Their total is 75. The probability is 75 over 130. I want to pause here and remind you that you don't have to tackle the complexities of probability on your own. For expert tuition in IB, A-Level, and IGCSE curricula, contact DAR Tutors. Our dedicated tutors can provide personalized support to help you achieve your academic goals. That's DAR Tutors. You can find our contact details on our website. Now let's move to a different way of thinking about probability. Theoretical probability. While experimental probability relies on observation, theoretical probability relies on logic and symmetry. It predicts what we expect to happen, not what has happened. A key concept here is the sample space, U. This is the set of all possible outcomes for an experiment. An event, A, is a subset of the sample space consisting of outcomes that share a specific property. We can think of this using set notation from Chapter 2. The sample space is like the universal set U, the outcomes are its elements, and an event is a subset of U. Let's use an example. We roll a six-sided die once. The sample space U is the set of numbers from 1 to 6. Let's define event A as rolling a prime number. The outcomes for event A are 2, 3, and 5. This can be visualized with a Venn diagram. The rectangle is U, containing all 6 outcomes. The circle is A, containing the prime outcomes. What about the outcomes that are not in A? We call this the complementary event. The complementary event, denoted a prime, is the event not A. It contains all the outcomes in the sample space that are not in A. In our case, a prime is the set 1, 4, 6's. Notice that event A and its complement A prime, when combined, make up the entire sample space U, and they cannot happen at the same time. The fundamental formula for theoretical probability requires that all outcomes in the sample space are equally likely. The probability of an event A occurring, written P of A, is the number of outcomes corresponding to the event A divided by the total number of outcomes in the sample space U. Let's use our die roll example. The sample space U has 6 outcomes, so NU is 6. Event A, rolling a prime number, has 3 outcomes, so NA is 3. The theoretical probability of rolling a prime number is therefore NA divided by NU, which is 3 over 6, or simply 1 over 2. This formula is the cornerstone of all the theoretical probability we will study. Let's explore some key properties of complementary events. Recall that a complementary event, a prime, is not A. Because an event must either occur or not occur, and these two possibilities cover the entire sample space and cannot overlap, the sum of their probabilities must be 1. That is, P of A plus P of A prime equals 1. This gives us a very useful shortcut. If we know the probability of an event P of A, we can find the probability of its complement, P of A prime, by simply subtracting from 1. So P of A prime equals 1 minus P of A. Let's illustrate with an example. Suppose we have 12 tickets in a basket, 3 green, 4 yellow, and 5 blue. What is the probability of selecting a green ticket? There are 3 green tickets out of 12, so P of green is 3/12 or 1/4. What is the probability of not getting a green ticket? This is the complementary event. Using the formula P of not green is 1 minus P of green, which is 1 minus 1/4, giving us 3/4. We can verify this. Not green means it must be either yellow or blue. There are 4 yellow plus 5 blue equal 9 tickets that are not green. So the probability is 9/12, which simplifies to 3/4. Both methods yield the same result. Mastering this relationship is a powerful tool for solving probability problems efficiently. We can represent complex experiments with multiple steps or components using visual tools like 2-dimensional grids and tree diagrams. Let's illustrate the outcomes of tossing 2 coins. The sample space is heads heads, heads tails, tails heads, and tails tails. A 2-dimensional grid is useful when there are 2 independent operations. We can make the rows for the first coin and the columns for the second. The points of the grid represent all possible outcomes. A tree diagram is especially useful when the experiment has several sequential steps, and the number of outcomes can become large. Let's extend this to a more complex scenario. Consider spinning a 4-sector spinner, where 2 sectors are blue B and 2 are white W, and spinning it 3 times. The sample space would be BW cubed, giving 8 possible outcomes. A tree diagram shows this clearly. The first set of branches is for the first spin, the second set for the second, and so on. We can then follow each branch to list all 8 outcomes. Now, let's find the probability of the event obtaining blue twice. We simply count the outcomes on our diagram that contain exactly 2 Bs. We find 3 such outcomes, BB and WBB. Out of 8 total outcomes, the probability is 3/8. 2-dimensional grids are particularly powerful for problems involving 2 dice. A standard grid will show all 36 equally likely outcomes. The grid cells represent the outcomes as ordered pairs, like 1-1 or 6-6. Let's use this grid to answer some probability questions. Part A, find the probability of rolling a sum of 11. First, we locate all the outcomes on the grid that add up to 11. These are 5 of 6 and 6 of 5. There are 2 such outcomes. Since there are 36 outcomes in total, the probability is 2 over 6, which simplifies to 1 over 18. Part B, find the probability that the result is an odd number. We can find this in 2 ways. First, by counting. For an odd product, one die must be odd and the other must be odd. The outcomes with both components odd are highlighted here. Counting them gives us 9 outcomes. So the probability is 9 over 36, or 1 over 4. The alternative, and often faster method, uses the complementary event. The complement of getting an odd product is getting an even product. A product is even if at least one of the factors is even. By counting the outcomes where at least one number is even, we find there are 27 such outcomes. So P of even is 27 over 36. Then P of odd is 1 minus 27/36, which is 9/36, or 1/4. This confirms our previous result. This demonstrates the utility of grids and complementary events in solving dice rolling problems. Finally, let's look at how Venn diagrams can be used to calculate probabilities for 2 or 3 events. Consider a class of 30 students. We are told that 19 study physics, 17 study chemistry, and 15 study both. The most important rule when constructing a Venn diagram is to fill in the intersection first. So, we place the 15 students who study both in the overlapping region of the 2 circles. Next, we find the number of students who study only physics. This is the total number in physics, 19, minus the 15 who study both, which gives 4. Similarly, for only chemistry, we calculate 17 minus 15, which is 2. We're not done yet. We also need to find the number of students who study neither subject. First, we sum the numbers within the circles. 4 plus 15 plus 2 equals 21. Since there are 30 students in the class, 30 minus 21 gives us 9 students who study neither subject. These are placed outside the circles. Now our Venn diagram is complete and accurately represents the entire class. We can use it to answer any probability question. For example, the probability of a randomly selected student studying only physics is 4 over 30. The probability of studying chemistry but not physics is 2 over 30. The probability of studying at least one subject corresponds to the total number of students inside the circles, which is 21. So the probability is 21 over 30. Let's summarize the key concepts we've covered today. We started with the definition of probability as a number between 0 and 1. We distinguished between experimental probability, based on observed data and calculated as relative frequency, and theoretical probability, based on equally likely outcomes and calculated as the ratio of favorable to total outcomes. We also learned about the importance of sample spaces and complementary events, and saw how visual aids like two-way tables, grids, and Venn diagrams are essential tools for solving complex probability problems, especially at the HL level. To test your understanding and hone your problem-solving skills, we've prepared a set of practice questions. Work through them carefully, and you can find the detailed solutions that follow. Practice is the key to mastery in probability. Here's your first practice question. A random survey was conducted to find the number of people in households. The results are summarized in this frequency table. Calculate the probability that a randomly chosen person lives in a household with exactly 2 people. Pause the video here and try to solve it on your own. Then you can resume to see the full solution. Welcome back. Let's walk through the solution. The question asks for the probability that a person lives in a household with exactly 2 people. This is an experimental probability problem, so we use the frequency from the table. The frequency for 2 people is 76. The total number of trials, or households surveyed, is given as 200. Using our formula, the probability is the frequency of the outcome divided by the total number of trials. This is 76 divided by 200. To simplify, we can divide the numerator and denominator by 4, giving 19 over 50. As a decimal, this is 0.38. So, the probability that a randomly chosen person lives in a household with exactly 2 people is 0.38. Here is practice question number 2. There are 25 students in a class. 15 of them have a cat, 10 have a dog, and 6 have both. What is the probability that a randomly selected student has neither a cat nor a dog? Pause and attempt this problem using a Venn diagram. Then watch for the solution. Let's work through the solution for this Venn diagram problem. The first step is to draw a Venn diagram and label the universal set U and the 2 events, C for cat and D for dog. Remember the rule, start with the intersection. We know 6 students have both a cat and a dog, so we write 6 in the overlapping region. Next, we find the number of students who have only a cat. That's the total number of cat owners, 15, minus the 6 who own both. This gives us 9. Similarly, for only a dog, it's 10 minus 6, which is 4. Now we calculate how many students are inside the circles. 9 plus 6 plus 4 equals 19. The total class size is 25, so 25 minus 19 equals 6 students who have neither. This number goes outside the circles. Now we can answer the question. The question asks for the probability that a student has neither a cat nor a dog. From our diagram, we see that 6 students fit this description. The total number of students in the class is 25, so the probability is 6 over 25, or 0.24. This shows the clear visual path that a Venn diagram provides. Here is practice question number 3. A biased coin is tossed. The probability of getting a head is 0.7. If the coin is tossed twice, what is the probability of getting at least one tail? This is a great opportunity to use complementary events. Think about what at least one tail means and its complement. Pause the video now. Let's find the solution to this problem. First, we need to know the probability of getting a tail. Since we can only get heads or tails, the probability of tails is the complement of heads. So, P of tail equals 1 minus 0.7, which is 0.3. The event at least one tail means we could get one tail or 2 tails. The possible outcomes that satisfy this are HT, TH, and TT. It's often easier to find the probability of the complement. The complementary event, no tails, means getting heads on both tosses. This outcome is HH. For independent events like coin tosses, the probability of both happening is the product of their individual probabilities. So P of HH is 0.7 times 0.7, which is 0.49. Now we use the rule for complements. The probability of our original event, at least one tail, is 1 minus the probability of its complement. That's 1 minus 0.49, which equals 0.51. Practice question number 4. Two spinners are spun. Spinner A has numbers 1, 2, 3. Spinner B has numbers 1, 2, 3, 4, 5. The scores are multiplied together. To solve this, a two-dimensional grid is the most helpful tool. Create the grid and count the favorable outcomes. Pause now to try it. Let's find the solution for this spinner problem. We need to create a two-dimensional grid to map out all possible outcomes. Spinner A has 3 possible outcomes, and spinner B has 5. This means our grid will be 3 rows by 5 columns, for a total of 15 outcomes in the sample space. Each cell will contain the product of the corresponding row and column numbers. Our goal is to find the probability that the result is greater than 6. This means we are looking for products of 7, 8, 9, 10, 11, 12, 13, or 15. Let's identify these outcomes on our grid. We can highlight all the cells where the product is greater than 6. We find these outcomes. Left parent 2 times 4. Right parent equals 8. Left parent 2 times 5. Right parent equals 10. Left parent 3 times 3. Right parent equals 9. Left parent 3 times 4. Right parent equals 12. And left parent 3 times 5. Right parent equals 15. There are 5 such outcomes. So we have 5 favorable outcomes out of 15 total outcomes. The probability is 5 over 15, which simplifies to 1 over 3. So the probability that the result of multiplying the two spinners' scores is greater than 6 is 1/3. Here is our 5th and final practice question. A group of 50 employees were surveyed about their interest in 3 areas: music, sport, and computers. The results are shown in the Venn diagram. Find the probability that a randomly selected employee is interested in music or sport. This problem requires careful reading of the diagram and understanding what music or sport means in a Venn diagram context. Pause the video and give it a try. Let's find the solution to this 3-circle Venn diagram problem. The question asks for the probability that an employee is interested in music or sport. Remember, music or sport means any area within the music circle, any area within the sport circle, or any area in their intersection. We need to sum up the values in all regions of the diagram that are part of either the music or sport circle. Looking at the diagram, the regions included are 6 music only, 4 music and sport only, 7 sport only, 20 music, sport, and computers, 7 music and computers only, and 1 sport and computers only, and sakisets. Adding these numbers together gives us 45. This means 45 employees out of the 50 surveyed are interested in music or sport. The total number of employees is 50. So the probability is 45 divided by 50, which simplifies to 9 over 10, or 0.9. This problem highlights the importance of carefully identifying the correct regions in a Venn diagram when dealing with the OR operator. Thank you for watching this video on probability for IB applications and interpretation higher level. We hope the detailed explanations, worked examples, and practice questions have helped clarify these essential concepts. Remember that probability is a foundational topic, and a solid understanding is crucial for the rest of the course. The key takeaways are to always understand your sample space, differentiate between experimental and theoretical probability, and master the tools like Venn diagrams and two-way tables for complex problems. If you found this video helpful and are looking for more in-depth, personalized support, please don't hesitate to reach out to us. Contact DAR Tutors for expert online or home tuition in IB, A-Level, and IGCSE subjects. Our tutors are ready to help you build confidence and achieve your academic goals. Thank you again, and happy learning.